Yes, they are precessing. In the environment that we're in, and what's causing them to precess in the room that we're in? The Earth's magnetic field. Perfect. Perfect. So the Earth's magnetic field is causing our atoms to precess. Now, are our atoms precessing in alignment with one another? No. There's not a strong enough magnetic field causing them to align. So they're randomly aligned in this environment here. So when the human body is exposed to the Earth's gravity, the body's hydrogen atoms, among other atoms that have magnetic moments, will precess. Precession is that wobbling motion that occurs when exposed to an external magnetic field. So again, that spinning top, spinning on its own axis, but again, when it's subjected to a magnetic field, it wobbles about the magnetic field. Just as that spinning top will spin on its own axis as long as it can. But when it starts to slow down, the Earth's gravity begins to pull on it and it begins to wobble. Same principle occurs here. So atoms will not precess in phase with one another, nor will they align with one another due to the weak magnetic field. The Earth's magnetic field is about a half Gauss to about 7/10 of a Gauss. 7/10 of a Gauss on the equator, at the poles, and about a half a Gauss at the equator. So one of the things that we need to be able to do in imaging is we need that alignment. We need to have a volume of atoms that are in a particular direction so that we can disturb them and see how long it takes them to get back into alignment. So what do we have to do in order to get these atoms aligned? We're going to have to apply a magnetic field. So the atoms will remain randomly aligned until a strong enough external force causing them to align in a particular direction. So here's an example. We have no external magnetic field. We have the atoms pointing in all directions. And because they're pointing in all directions, if they were to give off their signal, they would give off their signal in all directions as well. What did we say? We transmit and receive perpendicular to the static magnetic field. So we need to manipulate these atoms so that they're going to respond, giving their signal off perpendicular to the magnetic field as well. Okay. So we have our magnet that we have purposely set up to create homogeneity, and we put our patient into our magnet. When we do that, the atoms that were randomly aligned now line up. Some line up with the magnetic field, some line up against the magnetic field. Now, the magnetism that we use in MRI is created from various sources. The main magnet creates a static magnetic field. That's that homogeneous magnetic field that we use. Our gradient coils create a gradient magnetic field. Another name for a gradient magnetic field is time varying magnetic field. Time varying magnetic field. TVMF. Time varying. Why? Because that magnetic field is going to vary based on how we turn on the gradient. Magnetic field is homogeneous until we turn the gradient on. The more enhancement we get in T2 contrast. So in essence, what happens is the longer the TE, the more time we allow to have the tissues that are decaying to begin to separate. And so some structures will be bright, if they have a long T2 relaxation time, such as CSF. And then some tissues will decay very rapidly and will give us a dark signal. And so we will have a big difference in contrast between those tissues the longer the TE time, okay? So we use short TEs to minimize that T2 contrast. And as we talked about with TR, the shorter the TE, the more signal we have available to allow that image quality to be as high as possible. So the short TEs allow for high signal. The long TEs allow for high T2 contrast. So in our images here, we have a TR of 2000 with a TE of 20. And then we have an image here with a TR of 2000 with a TE of 30. And again, you can see the difference in the images. That 10 millisecond TE isn't very high, but in essence, we are able to discern a little difference in that. Okay. Now, here's an image where the TE time really makes a big difference. We're looking at two images here. We have this image here on this side uses a TR of 3000 with a TE of 30. The image on the right is a TR of 3000 with a TE of 90. Now, what I'd like to ask you, first of all, is remembering your parameters yesterday. If we use a TR of 3000 with a TE of 30, which is a relatively short TE, what type of an image do we generate with a long TR and a short TE? Proton density. So this image here on the left of the screen is a proton density weighted image. And all of the contrast that we're seeing here is based on proton concentration. We can see again that gray matter has high proton concentration compared to white matter. We can see here that fat has a high proton concentration as well. And CSF has higher proton concentration as well. So here we're looking at an image that is a proton density weighted image. The image on the right uses a TR of 3000 and with a TE of 90. So in essence, that is a long TR with a long TE. What type of image do we generate with a long TR and a long TE? T2 weighted image. So in this example, we have a proton density weighted image and a T2 weighted image. Now, they can be very helpful to us. And again, here we are dealing with our TE times. Both of the TRs are the same. So in this particular example, we acquired each slice with 2 images per slice. One proton density weighted with the 30 TE, one T2 weighted with the using a 90 TE. Now, how does it benefit us? You can see here that fat is bright on the TE of 30. By the time we get to a TE of 90, look what's happening to fat. Fat is starting to decay. So since that is happening at a TE of 90, we can say that fat has a T2 close to 90 milliseconds because it's decaying at 90 milliseconds. So that's given us one of the bit of information in that the T2 of fat is relatively short comparatively, compared to other tissues, that is.